This is the video for section 8.3 on applications to physics and engineering. And this section contains two primary applications. We're only going to discuss one in this class, and that's the topic of moments and center of mass. We're not going to deal with the force due to hydrostatic pressure. So the idea with a moment or a center of mass is that if you cut a flat sheet out of, say, plastic or metal, some uniform material, so instead of a sheet we would call it maybe a flat plate, or in the business they call this a lamina. Then as long as the shape is reasonable, it has some sort of balancing point. Now the technical term for a balancing point is the center of mass, or the centroid. And this is called the center of mass because if you were to treat this lamina as a point mass, as you frequently do in physics or engineering problems, then the centroid is the location of the point that would encompass all the mass. And so there are formulas for computing this directly, and I'll go ahead and write those down in the case where, so if we're looking at a region like we usually do, that's described by the graph of a function y equals f of x, say from endpoints A to the endpoint B, then the relevant formulas are the following, and we need to make one assumption, is that the lamina has uniform density and that density is rho. That's the Greek letter rho, not a p. And then we have the following formulas. So m sub y is the moment for the lamina about the y-axis, and that is given by the formula rho times the integral from a to b, x times f of x dx. And the m sub x, which is the moment about the x-axis, is given by a similar formula: multiply by rho, take the integral, but it's the integral of 1/2 f of x squared dx. And the term moment is not as in a moment in time, but there's a physical notion of a moment that we'll discuss when we explain the derivation of these formulas. Now the total mass of the lamina can be obtained as taking the density of the material times the area of the lamina. That's because the density is uniform, and so one can get this as rho times the integral from a to b f of x dx. And then the center of mass, or the centroid, x bar is our notation for the x-coordinate of the centroid, or the center of mass, and that is gotten strangely my over the total mass, which simplifies to the formula 1 over a times the integral from a to b x times f of x dx. Right, so that comes from taking the formulas for the moment here, dividing by the formula for the total mass here, and canceling the factor of rho. And similarly, y bar is the y-coordinate of the centroid. That's given by the formula moment with respect to the x-axis over the total mass, which simplifies to 1 over the area times the integral a to b 1/2 f of x squared dx. So what I'm going to do in the next couple of pages is to explain where this formula comes from, because these formulas, I don't know about you, but they look like they come from nowhere compared to things that we've looked at previously. I mean, the only one that seems at all reasonable is the total mass formula. And why should the center of mass be given by these weird formulas? So in order to understand where the formulas for the center of mass come from, we're going to look at a simple case. And that's the simple case of a lever or a lever. Oof, that word is lever. In other words, what we're going to consider is a teeter-totter or a seesaw. Okay. And so we're going to consider the lever with 2 point masses. And a fulcrum where the point masses are balanced. So a fulcrum is a balancing point, and that's exactly the same thing as a centroid, or a center of mass in our situation. So here's your lever with the first point mass having mass m1, the second point mass having mass m2, and maybe if the m1 is a little bit bigger than m2, then the fulcrum needs to be a little bit to the left. If you've ever played on a seesaw before, you know that if the seesaw is balanced exactly in the middle and one person is heavier, then the heavy person drops down and the lighter person goes up. And you can compensate this by moving the location of the heavier person inward in order to create a balance. Now, if the distance from the first point mass to the center where the fulcrum is d1, and the distance from the fulcrum to the second point mass is d2, then we have what's called the law of the lever, that says that the balancing point needs to be exactly when the product m1 d1 is equal to the product m2 d2. Okay? And these two products are called are related to the moments of the system. Now, we don't like to think about these things in this level of abstraction, what we tend to do is think about what happens if the lever is on the coordinate axis. So we're going to now move this to the x-axis. And now we'll look at mass number 1 sitting at a point x1, mass number 2 sitting at a point x2 relative to the origin, and then the fulcrum is somewhere in the middle, say at a point x bar, right? And this goes with the notion that we had previously of this being related to the center of mass. And then if you translate the law of the lever in terms of what these distances are here and here relative to the numbers x1, x2, and x bar, what we have is that m1 times x bar minus x1, that's our d1, equals m2 times x2 minus x bar, that's our d2. And if you solve this for x bar by multiplying out the quantities, moving the x bar bits over to one side, the non-x bar bits over to another side, and solving for x bar, then we get that x bar can be written as m1 x1 plus m2 x2 divided by m1 plus m2. And on the top of this, so you should note a couple of things. First of all, the denominator expression is exactly the total mass of the system, assuming that the mass of the lever is negligible. Then the total mass of the system is just the sum of the 2 point masses. And the numerator is what we call the moment of the system about the origin. Okay. And if you like, and the book does like, this is precisely the sum of the individual moments in other words, this system with 2 point masses, excuse me, the system with 2 point masses has 2 individual moments, precisely the first term m1 x1 is the first moment, and the term m2 x2 is the second moment of the system. And it is a fact, although we won't explain exactly why it's true, is that if you have more masses on the lever, so say we have a total of n masses on the lever that are with distances we should specify with x coordinates x1, x2 to xn, then the fulcrum, the balancing point, is going to be precisely x bar, which is going to be a big fraction, m1 x1, m2 x2, up to mn xn, Right? So similar to the formula we had in the case of 2-point masses, we take the sum of the individual moments in the numerator of the expression and then the sum of the individual masses in the system in the denominator. And we will frequently denote by m, as we did on the previous page. The total mass in any situation is denoted by m. Now, the situation is almost exactly the same on the next page, where we look at some masses that are not on a single line but are actually in the coordinate plane. So I'll draw this with 3-point masses. Say that M1 is over here in the first quadrant. It has x-coordinate x1 and y-coordinate y1. Maybe the second point mass is over here in the quadrant over here. It has mass M2, x-coordinate x2, and y-coordinate y2. And let's say maybe the third one is up here in the second quadrant, mass M3 with x-coordinate, sorry, that's the y-coordinate y3 and the x-coordinate x3. Then, right, so there's a lot of items in this picture. We have 3 quantities that are relevant for the computation of the center of mass, and that is the moment about the y-axis, my, and this is just like the moment that we had with respect to the origin in the previous page. This is the sum of the x-coordinate moments of the individual point masses. So if I have 3 of them, I would have m1 x1, m2 x2, and add that to m3 x3. In general, I'll have n point masses, and so I'll add this up to mn xn. And this can be written concisely using the summation notation. I equals 1 to n mi xi. Right. And so this is starting to look even more like a Riemann sum, where an integral will take place. Similarly, m sub x is the moment about the x-axis. And this can be written as the summation I equals 1 to n of the mi yi's, obtained in exactly the same format. And then if the total mass is the sum of the individual point masses, then the x-coordinate of the centroid, or the center of mass, is gotten by taking the moment with respect to the y-axis, that's the one that uses the x-coordinates, and dividing by the total mass of the system, and then y bar, which is the y-coordinate, is the moment with respect to x divided by the total mass. And as I said before, the alternate interpretation of the fulcrum point is that if this system were to be perceived as a point mass, then these would be the coordinates of the point that would describe this system as a point mass. Now we're almost to the point where we can derive the formulas for that I gave you on the first page for the centroid of a lamina. So I'm in the situation of a lamina that's described by a non-negative function f of x in the range of x equals a to b. And what we're going to do is we're going to approximate this as we do with all sorts of integrals. We're going to approximate the lamina by small rectangles. So this has uniform density rho, and I'm going to approximate by rectangles following the protocol of the midpoint rule. Right, so I have n rectangles with width delta x, which is b minus a over n, and the ith rectangle midpoint is denoted by xi bar, and then the height of that rectangle is gotten by taking that midpoint and plugging it into the function. And so in my picture here, maybe my little rectangle looks like this, which I'll look at a much larger version of over here. So the x-coordinate for the center of that rectangle is xi bar. The height of the rectangle is f of xi bar. And now if life is at all reasonable, if you have a rectangle with a uniform density rho, then the center of mass of that rectangle should be exactly the center of the rectangle. So the x-coordinate for the center of mass should be exactly the midpoint, and the y-coordinate should be exactly the midpoint as well, which occurs at half the height. Okay. Now, that's the center of mass of the rectangle. That is the point where the mass would be concentrated if we treated this as a point mass. And if we treat this as a point mass, then we can talk about the specific moment of this point mass. And we can talk about the moment with respect to the y-axis. WRT stands for with respect to, so that would be exactly mi times xi bar, right? This is exactly the formula that we had for the moment of a point mass with respect to the y-axis. Now xi bar is the midpoint that we've been given. Mi is the mass of the individual rectangle, and remember this is just an approximation of the piece of lamina. So the mass we would get here is exactly rho times the area of that ith rectangle, and then times the x-coordinate, xi bar. And the area of the rectangle is very easy to compute. It is the width of the rectangle times the height of the rectangle. So we end up with MIXI is rho times delta x, that's the width, times the height, which is f of xi bar, times then that x-coordinate xi bar. Okay. And that tells us that the total moment of the system with respect to the y-axis, that's what we would call my, and this is an approximation in terms of the rectangular approximation, so that would be the summation I equals 1 to n of the MIXI bars, which, since we have the expression up above here, this is precisely the sum, I equals 1 to n, and I'm going to rearrange the terms. It's rho times xi bar times f of xi bar times delta x. And this looks exactly like a Riemann sum. It is a Riemann sum, and once we take the limit of the Riemann sum, we get that the actual moment of the system with respect to the y-axis, my, is exactly the integral from a to b of rho times x times f of x dx. Now, similarly, the total mass which is m, can be gotten approximately as the sum of the masses the sum of the individual point masses, and using the formula that we had up above there for that's the mass of the ith rectangle, we get that this is the summation I equals 1 to n of rho times f of xi bar times delta x. And when we take a limit of this Riemann sum as n goes to infinity, then we get that m is exactly equal to the integral from a to b of rho times f of x dx. And if you pull rho out of the integral formula here, you see that the integral that's left, right, rho is constant because the density of the lamina is uniform, so it can come out of the integral, and we're left with the integral that represents the area of the lamina. Last derivation, and then we'll do an example. I want to explain why the moment with respect to the x-axis is what it is. So redrawing the rectangle that we had here, right, the x-coordinate of the center of mass of the rectangle was xi bar, and the y-coordinate of the center of mass of the rectangle was 1/2 f of xi bar. And so the moment with respect to the x-axis of this individual rectangle is gotten by the mass of the rectangle times the y-coordinate, right? And so the mass, again we computed previously, is rho times delta x times the height of the rectangle, so f of xi bar, And now we're multiplying by the y-coordinate, which is 1/2 f of xi bar. And so the total moment with respect to the x-axis, that's our m sub x, is approximately the sum I equals 1 to n of the individual moments. Rearranging the terms that we have in the expression for mi, yi above there, we have the summation I equals 1 to n of rho times 1/2 times f of xi bar squared times delta x. So when I take that Riemann sum, take the limit as n goes to infinity, we find that the mx is exactly the integral from a to b rho 1/2 f of x squared dx. And then we can put those in with the formulas for the center of mass, the centroid, to again find that x bar is my over m, and we write that as 1 over a times the integral from a to b x times f of x dx, as we saw on the first page, and y bar is m sub x over m, which cancels to 1 over a times the integral from a to b 1/2 f of x squared dx. Let's see an example. So in this example, we're asked to find the centroid of the region bounded by some curves. And those curves are, that's the word curves, y equals square root of x, y equals 0, and x equals 4. Now, in general, what you'd like to do is to sketch the region to make a reasonable guess about where the centroid should be. So there's the curve y equals square root of x, there's the line x equals 4, and here's the point x equals 2, the point y equals 1. And what you notice when you inspect this region, I'm going to cut it into 4 pieces, that the upper left-hand piece doesn't have very much of the mass in it. The upper right-hand piece has more of the mass, and the lower left-hand piece has a little bit more of the mass, but the bottom right-hand piece has the majority of the mass. So we guess that the centroid is somewhere in that bottom right-hand piece of the region. So that's going to inform our decision about whether we got a reasonable answer. So we're going to guess that x-coordinate is greater than 2, right? And the y-coordinate is less than 1, because that's what it means to be inside that lower right-hand piece of the lamina. Good. Now we just go and compute. So the area, integral 0 to 4, square root of x dx. Square root of x is x to the 1/2, so the integral there is 2/3 x to the 3/2. Evaluate it from 0 to 4, so 2/3 times 4 to the 3/2. Square root of 4 is 2, 2 cubed is 8, So we have 2/3 times 8, or 16/3 for the area. Our formula for the x-coordinate of the centroid says to take the reciprocal of the area times the integral from a to b, so 0 to 4 of x times f of x dx. So we're going to put in our expression for a. The reciprocal of that is 3/16. Integral from 0 to 4 of x times the function f of x, which is square root of x, so x to the 1/2 dx. We integrate this by combining the exponents. X times x to the 1/2 is x to the 3/2. And integrate that by raising the exponent by 1 and multiplying by the reciprocal of the new exponent. New exponent is 5/2, so I multiply by 2/5. Evaluate from 0 to 4. Simplify the coefficient by canceling the 2's, or 2 and a 1, 2 from the 16's. So we have 3 over 8 times 5, which is 40, times 4 to the 5/2. And square root of 4 again is 2, 2 to the 5, 2, 4, 8, 16, 32. Let's write that as 3 times 2 to the 5th over, that's 5 times 2 cubed, and so we can cancel 3 factors of 2 here, and we're left with 2 to the 2 in the top. So x bar is 3 times 4, which is 12 over 5, and that simplifies to 2.2, which is slightly larger than 2, as our guess allowed us to believe. Similarly for y bar, we have 1 over a integral from 0 to 4 of 1/2 times f of x squared dx. So that's again the reciprocal of the area, 3/16 times the integral from 0 to 4 of 1/2 square root of x squared dx. I'll bring out the 1/2, and so we get 3 over 32 times the integral from 0 to 4 of x dx. So that's 3 over 32 x squared over 2, evaluated from 0 to 4. And so that y bar coordinate is 3 over 32 times 4 squared is 16, over 2 is 8. And then we cancel a little bit. 8 cancels with 32 to leave a 4 in the denominator. So we end up with y bar equals 3/4, or 0.75, which is slightly smaller than 1, as we predicted. So in the end, our centroid is the ordered pair x bar, y bar, which is 2.2 for the x-coordinate and 0.75 for the y-coordinate. Two more items for us to consider in this section. First of all, you can see more examples like the previous one in examples 4 through 5 of the section. There's a more general situation, as we saw with areas and lots of other regions, where the region is bounded by two curves, maybe f of x on top and y equals g of x on the bottom, still going from A to B. And in that case, we're not going to do the entire derivation here, but the x-coordinate of the centroid is still 1 over A times the integral from A to B of, now the function has to involve f of x and g of x, so we have x times the difference, fx minus g of x dx. And the y-coordinate, similarly, 1 over the area times the integral from A to B of 1/2 times the difference of the squares of the functions. And if you like, you can read a little bit about the derivation for this. It's in exercise 86 or something like that. And you can look at an example of a computation in example number 6 using this formula. Right, so the centroid of a lamina represents the balancing point for the lamina. There's a very useful application of this that we want to end with here, and that's called the theorem of Pappus. And that says that if you rotate a region R about a line L, and it's any line L, it can be horizontal, vertical, or diagonal, as long as the line has R entirely on one side of it. And then you have a very nice formula for the volume of the solid of revolution. It's V equals A times D, where A is the area of the region and D is the distance traveled by the centroid when it's rotated about the line. And we'll draw a picture of this when I do an example on the next page. So, in an example, I want to rotate the region from the previous example about the line x equals 6. So pictorially, I have my region 2, 4, 6, 2. So y equals the square root of x, y equals 4. And the centroid we found was somewhere around here. And I'm going to rotate about this line x equals 6. So I need a mirror image copy of my region. Like so. A mirror image of the centroid of the region. I rotate my region, rotate like so, and I track the rotation of the centroid. So the centroid, like every other point in the rotation, will follow the path of a circle. So the volume formula from the theorem of Pappus says that I need to figure out what the area is, and I need to figure out what the distance traveled by the centroid is. We saw previously that the area was 16/3, and now the distance traveled by the centroid is going to be the circumference of the circle determined by the location of the centroid and the center of the rotation. So it's going to be 2 pi r, where I'll draw a picture of r right here. So it's the radius from the center of the rotation to the x-coordinate of the centroid. And so that value for r is going to be the right-hand x-coordinate minus the left-hand x-coordinate. And so that gives us that r equals 3.8. And so the distance that we travel is 2 pi times 3.8. And when we plug these two pieces, there's the d, there's the a, into a times d, we find that the volume is 16/3 times 2 pi times 3.8, which is a pretty easy way to compute the volume of a solid of revolution instead of having to go through and evaluate it by washers or shells. You can see another example of this in the textbook in example number 7, and this is the end of the lecture on section 8.3, Applications to Physics and Engineering.